Okay, you can actually choose harmonic oscillator. And then here I'm gonna basically clear one. I'm gonna just activate just one wave function. Okay. So let us look into this one. This is a probability density function. Okay, so for the ground state energy, and then I can actually increase further here. Let's kind of look into this one. Let me just kind of lower it. Okay, so this is again, the ground state probability density function. If I increase further, you see this is a yellow, and so on. Okay, so if we increase the energy, it has more peaks, and also, I mean, if I look at actually this particular energy here, so in this case, this is essentially classically where you can extend as far as you can, right? But if we look at probability density function here, there is still non-zero value, right? I mean, this is yellow color. Maybe you might not be able to see it. I'm going to click this one. Okay? So in this case, beyond the point where classically possible, right? Now there is non-zero value, right? So what that means is that, quantum mechanically, there is still a chance that you can find this mass outside of, the classically possible. Okay? And also, if we look at, higher energy here, for example, in this case, as we saw before, the probability density function looks like kind of parabola, right? Like classically you would expect. Okay? So, and also, let us look into this one. Like, for example, for the classical harmonic oscillator, when the energy is lowest, you would expect mass staying at the equilibrium position, okay, the initial position, right? And then if you apply that to quantum mechanics here, this is the ground state energy, and then look at the probability. Probability is maximum at x equals 0, right? So this is the kind of initial position, right? Initial position before any movement, right? And then now, when we give like some excitations, if you look at kind of like E1, now it's kind of moving back and forth, the probability at 0 point drops significantly, right? I mean, in this case it's 0. And then if you can actually look at other points here too, like now it kind of oscillates here, like for E is 3, now probability, I mean, is non-zero, but again, at 0 point is lower than other probabilities. Okay, so that is also kind of something you can kind of expect here. Okay, so so anyways, here, like again, you can kind of modify this potential energy width, and then you can look at more specifications here, like specified n, or even in this case, you can also play with the superposition state. Okay, so now I fixed the time, but if I run the time, again, because we are looking at a specific energy, just for that specific energy, we are looking at probability density function, or we are looking at just kind of one wave function, right? But you can actually superposition as well. Again, here, time independent, right? Now time is running, but probability density function does not change over time. But if we actually couple that, for example, in this case, 1, normalize it, apply. Now, if you look at probability density function, because two wave functions are coupled, now it has time-dependent probability density function. Okay, so what that means is that now you have to look at the position as well as the time. Okay, so if you really want to find out probability distribution. Okay. All right. Okay. So then that's it for today.